Hello everyone, my name is Zhang Xiaowen Gong. I am a final year PhD student from the IACOMA research group led by Professor Josep Torrellas in the University of Illinois at Urbana-Champaign. Today, I'm going to present SAVE, Sparsity-Aware Vector Engine for Accelerating DNN Training and Inference on CPUs. Sparsity is the zeros inside a data structure such as a vector or a matrix. The multiply accumulate operation or MAC has the form C equals C plus A multiplied by B, and it is the core computation in many algorithms. When there is a zero in one of its multiplicants, the MAC operation is ineffectual, meaning that the operation does not change the destination content. Therefore, we can skip it to improve performance. There are two types of sparsity in DNN workloads. The first type is activation sparsity, and the main source is ReLU. ReLU activates the output of a layer by setting the negative values to 0. The output from ReLU can be the input to the next DNN layer. The sparsity from ReLU is unstructured, meaning that there is no discernible pattern. It is also dynamic, meaning that different input may cause different sparsity patterns. ReLU typically induces 40 to 90% sparsity, which is too low for traditional sparse method to benefit. The second type is weight sparsity, and the main source is pruning. Pruning is a popular technique to reduce the size of a DNN. The sparsity from it is static in inference, but gradually increases in training. It can be either unstructured or structured depending on the pruning method. Exploiting unstructured sparsity is hard because it does not map to parallel hardware nicely. Some dedicated accelerators can leverage it, but there are few attempts to exploit it on general-purpose processors. We now discuss the general matrix multiplication, or GEMM. GEMM is the core computation in many types of DNNs, and it maps efficiently to multi-core SIMD hardware. Here is an example of a GEMM. It computes a 2x2 tile of C equals C plus A multiplied by B, and it uses two-way vectorized MAC operations. There are 4 steps to compute the tile. In each step, an element from A is broadcasted to all lanes in a vector. The vector is then element-wise multiplied by another vector from B. The result is finally element-wise accumulated onto a vector from C. And here is step 1. Step 2. Steps 3. And finally step 4. We observe different types of locality across steps in the example. First, the non-broadcasted vectors from B and C have temporal locality. As shown, the same vector is being used in different steps. Second, the broadcasted A elements have spatial locality. As shown, neighboring elements are broadcasted in different steps. In addition, sparsity can affect vector MACs differently. If a 0 is broadcasted to all vector lengths, all lengths are ineffectual, and therefore the whole vector MAC is ineffectual. We can skip the whole vector MAC to save work. We call this broadcasted sparsity. On the other hand, if a vector has some sparse lengths, only these lengths are ineffectual. We cannot trivially skip the whole vector operation. We call this non-broadcasted sparsity. To exploit both types of sparsity, we propose SAVE, Sparsity-Aware Vector Engine. SAVE combines effectual lengths from multiple vector MAC instructions and issues a compacted computation in CPUs. It only adds limited hardware to the existing CPU vector pipeline, and it is transparent to software. SAVE accelerates end-to-end training by 1.2 to 1.6x and inference by 1.4 to 1.7x. We make the following contributions. We propose the first sparsity-aware vector engine for CPUs that exploits both broadcasted and non-broadcasted sparsity. We identify and leverage the locality in the broadcasts and balance the load among vector lengths. Finally, we support mixed precision MAC operations. The basic technique in SAVE is called vertical coalescing. It can leverage both broadcasted and non-broadcasted sparsity. Here we give an example. I1 to I4 are vector mag instructions that compute C prime equals C plus A multiplied by B. The instructions do not depend on one another and are ready in the reservation station. Each instruction has 4 lanes. On the right-hand side, we have the accumulation base C, the multiplicand A that contains broadcasted values, and the multiplicand B that contains non-broadcasted values. Note that save does not require one of the multiplicands to hold broadcasted values. We fill the multiplicand in this way only to reflect the typical usage in GEMM workloads. The left-hand side is the accumulation destination C prime. Vertical coalescing takes effectual lengths from the instructions and assembles the temporary operands T. This is feasible when the front-end bandwidth is higher than the throughput of the vector unit, so that the reservation station is filled with vector instructions. This is common when executing GEMMs on desktop and server CPUs. Res contains the computation result from the vector unit. In the first step, we remove the instructions whose lengths have all completed. For each ineffectual lane, we copy the data from its accumulation base directly to its destination and treat it as completed. In the example, because A0 is broadcasted to all lanes in I2, all lanes in I2 are completed, so we remove I2. In step 2, for each lane I in T, save selects an effectual lane I from a ready instruction in program order. In the example, we first assign lane 1 from I1 to lane 1 in T. Then lane 2 from I4 to lane 2 in T. And then lane 3 from I1 to lane 3 in T. However, because there is no effectual lane 4 from these instructions, we cannot assign any lane to lane 4 in T. Note that the whole process is performed in a single cycle. In step 3, we compute a vector mag with T and produce the result in res. In step 4, we write each lane's result back to its proper destination. Lastly, in step 5, we mark all completed lanes. Recall that in step 1, we remove instructions whose lanes have all completed. Therefore, we can remove I1. The advantage of vertical coalescing is that it does not need expensive crossbars to permute lanes to different positions, so the hardware is simple. However, it can cause lane imbalance. As discussed, because there is no effectual lane 4 in these instructions, we cannot fill lane 4 in the T. However, there are still unscheduled effectual lanes from I3 and I4. This kind of lane imbalance is very common when operands are reused. For example, all these 3 instructions use B0 as a non-broadcasted multiplicand. Because the same vector has the same sparsity pattern, it is obvious that vertical coalescing can only schedule lane 1 in I1, but not the effectual lanes from I2 nor I3. To balance the lanes, save applies limited rotation to the operands. We call this rotate vertical coalescing. With this technique, operands in I2 are right rotated by 1 lane, and those from I3 are left rotated by 1 lane. After the rotation, all effectual lanes from these instructions can be scheduled. Besides rotation, we apply another optimization to further increase the rate of compaction. We notice that conventional vectorized dependence can have false dependence under save. This happens when 2 instructions share the same accumulator, such as in this example. Here, the accumulation base in I2 depends on the destination in I1 with a read after write dependence. As a result, I2 is not ready until I1 finishes. However, if we view each lane separately, we can see that the effectual lane 2 in I2 only depends on lane 2 in I1, so it should not wait for lane 1 in I1 to finish. We call this scenario a false dependence. To eliminate false dependence, save maintains dependence of each vector lane separately. In this way, lane 2 in I2 no longer depends on lane 1 in I1. We call this lane-wise dependence. We do not replicate the dependence hardware to support lane-wise dependence. Instead, we use a scheduling algorithm that adds small hardware overhead. Please refer to the paper for details. Next, we found that after save reduces compute, the the L1D read bandwidth can become a new bottleneck. We tackle this by leveraging the spatial locality in the broadcasts in GEMMs. We introduce a small high-throughput cache to capture this locality. We call it the broadcast cache. Only broadcast requests access this cache. All other memory accesses goes to L1 directly. We found that a 32-line direct mapped broadcast cache can already give over 90% hit rate. Recently, vendors have introduced mixed precision computation to accelerate DNN workloads. In a mixed precision instruction, the inputs have lower precision than the output. This allows more operations to be performed per fixed width vector without losing much network accuracy. We focus on the AVX512 bfloat16 dot product instruction. In this instruction, each 32-bit accumulator is mapped with two pairs of 16-bit multiplicants, and two consecutive maps are performed. First, the left multiplicand pair produces a product and accumulates onto the base. Then, the right multiplicand pair produces a product and accumulated onto the intermediate result. The final result is written back to the accumulator. Working with mixed precision is challenging. Our techniques so far only work when the whole two-step accumulation is ineffectual. This happens when both multiplicand pairs are ineffectual. In this case, we can skip the two-step accumulation. On the other hand, if only one of the multiplicand pairs is ineffectual, the two-step accumulation is still effectual as a whole. Therefore, we cannot skip it. However, we still want to skip the ineffectual MAC. To exploit sparsity in the mixed precision instructions, SAVE collapses bubbles in the multiplicand lengths from the instructions that share the same accumulator. In the example, both instructions accumulate onto C0. For simplicity, we only show one accumulator lane and the two pairs of multiplicand lanes mapped to it. First, we assign multiplicand lane 1 from I1 to multiplicand lane 1 in the T. Then, because multiplicand lane 2 in I1 is ineffectual, we collapse it. Therefore, we assign multiplicand lane 1 from I2 to multiplicand lane 2 in T. This compaction method guarantees that the original accumulation order is preserved. Therefore, the floating point computation results are consistent with and without the compaction. In addition, we make sure that the compaction supports precise exception. Please refer to the paper for details. The last technique SAVE employs comes from the observation that server CPUs often have multiple vector units, and the vector units are power hungry. With SAVE at high sparsity, there are insufficient effectual lengths to keep all vector units busy. Consequently, SAVE can disable some of the vector units and then increase the core frequency according to the sparsity level. We implemented SAVE in the Sniper multi-core simulator. The baseline resembles a 28-core Skylake server CPU with AVX512 vector extension. We evaluated SAVE on training and inference of multiple networks with realistic sparsity. These networks are trained with or without pruning. The networks are executed with MKL DNN kernels and 28 threads. We evaluated both FP32 and FP32 BF16 mixed precision kernels. We now present SAVE's performance. The plot shows SAVE speedup over the baseline. The y-axis is the speedup. On the x-axis, each group of bars shows an evaluated DNN. In each group, we show SAVE speedup on FP32 training, mixed precision training, FP32 inference, and mixed precision inference. The results show that SAVE achieves significant speedup in all scenarios. For training, we obtain 1.2x to 1.6x speedup. For inference, we obtain 1.4x to 1.7x speedup. Finally, please refer to the paper for different designs of the broadcast cache, implementation details of each technique, and more detailed evaluations. In conclusion, we propose SAVE, the first sparsity-aware vector engine for CPUs. SAVE combines effectual lengths from multiple vector MAC instructions before issuing a compacted computation. It exploits both broadcasted and non-broadcasted sparsity. It is cheap in hardware and transparent to software. Finally, it supports mixed precision MAC operations. SAVE can accelerate both training and inference significantly. Thank you very much for your attention.